In our last lecture, we left off looking at a GPS unit and considering how GPS itself is related to Einstein's theory of general relativity. In this lecture, we will continue to look at concepts in physics, and an understanding of these will form the foundation upon which we build insights into the form of string theory. From here, we will continue on that developmental path, which we talked about last time, to devote 2 lectures to particle physics and the particle zoo, many of what we will call the denizens. These are particles that we've believed since 1950s were the building blocks of matter. Now remember, even though string theory goes one step further to postulate that what we think of as particle are actually oscillating strings, we still speak of and use particles such as gluons, quarks, and leptons in our discussions of string theory. So in lectures 4 and 5, we will spend some time working through this particle zoo, as physicists like to call it. And then we're going to head off and look at the dilemma that faced Stephen Hawking, a dilemma that involves black holes and led physicists to look further beyond the world of particles. Without this dilemma, physicists would have been perfectly happy to look at a worldview based on particles. Now, in this foundational lecture, we must begin, no surprise, with Albert Einstein and his great opus of 1916. The theory of general relativity, it's called. A major goal of this lecture will be to look at the sources of this theory, a theory that leads us to believe in the Big Bang and to an understanding of the cosmic microwave background. Already in 1905, Einstein had written several seminal papers. In our discussions here, one of these papers is going to be the most important. It's the one where he told us that space and time are flexible, that you could trade a little bit of space for a little bit of time, replace it with a little bit of time or a little bit of space, vice versa. Space could shrink, time could be made to slow down as you approach the speed of light. All of these things are very mysterious. In fact, scientists have observed them over and over again in the laboratory, so we know that they're an accurate description of our world. Einstein's approach to these things was, in fact, initially not very mathematical. He had to learn a lot of mathematics from Hermann Minkowski. In fact, it was Hermann Minkowski who gave us the picture that space and time are somehow connected in this thing that we now call the space-time continuum. A famous quote from Einstein is, "The secret to creativity is knowing how to hide your sources." He did a terrible job at this. The sources that give rise to the theory of general relativity actually existed well before Einstein's time. In fact, we can single out 4 individuals, 4 mathematicians, whose ideas were the major sources. Remember, we keep repeatedly in this series of lectures talking about how mathematics and science go hand in hand in making progress. The 4 mathematicians were not at all worried about anything in the real world in particular. Their names were Boole, Gauss, Lobachevsky, and Riemann. We're going to concentrate particularly on Riemann's ideas because he's the one who sort of sews this all up together. Now, before Riemann, mathematicians had thought that there was only one kind of geometry. This is the kind students learn in high school. For example, parallel lines never meet. The sum of the angles in a triangle must add up to 180 degrees. The area of a circle can be related to its diameter by a particular number called pi and a factor of a 4th. These facts are all related to the geometry that was first described by Euclid. The only problem with knowing these facts is that it's possible to define geometries where they are not true. Now, this may seem surprising, but let's go through this again. Remember, when I talk about mathematics here, I try to do it in terms of equations, but the equations are actually pictures. Remember, we have this alternative way of understanding the mathematics. So let's return to a bit of geometry, which I want to spend some time investigating because it's essential that I know you understand this before we turn to its extension, something called non-Euclidean geometry. We'll begin with Euclid's parallel lines. So let me pull up an animation. Here we see it. You'll notice that there are two dots on the screen. So if they're parallel lines, then we need some sort of motion. So let's set this in motion, and there we see the lines moving up. Now, Euclid would tell you as long as these lines are parallel, they will never meet each other. They'll just go on forever. And that's the sort of thing that we've seen in this animation. And you all also can see that we set up some grid lines here, both vertically and horizontally. And we can think of these green and purple lines as particles moving and leaving behind the trails so we can see their path. And sure enough, they never meet. I bet that doesn't surprise any of you. Parallel lines never meet. So, in a similar manner, we can look at triangles. Again, something that one learns in high school geometry. So let me pull up a triangle now. You see two dots to begin with, so I have to actually create a triangle. So let's go ahead and do that. Here we have our triangle. And you can see we're nicely forming a triangle. Now, what I'm going to do is to shade in green the area of the triangle. And remember, there's this device called a compass. And a compass is a device for measuring angles. So we can lay the compass along the angle on the right side of the diagram. We can lay the compass along the angle on the left side of the diagram. As well, we could lay the compass along the angle at the top. Now, when we do that, we get some numbers. And if you actually add all the numbers up, they add up to 180 degrees. Again, no big surprise. And now the final figure that we want to talk about is a circle. Actually, we're going to talk about a sphere, something more interesting than a circle. Because a sphere, well, you know, it holds a different kind of relationship for parallel lines. So let's see if we can actually generate this other picture. Let's start again with the parallel lines. Well, they look pretty parallel, but gee, they met someplace. Now, in the background of this animation, if you'll notice very carefully, I have put a planet. And so you can imagine two travelers starting on the equator saying, we're going to walk in a northward direction, directly north. And if they do so, when they first leave the equator, those look like parallel lines. Let's watch this again. So as they first leave, yep, the two lines look like they will never meet. But then suddenly, because they are on the surface of the Earth, eventually both of them will meet at the North Pole. And so it is not true all the time that parallel lines never meet. Here's an example where parallel lines do meet. And there's our planet. So that's one fact of geometry that is kind of curious. You might say, well, that's an exception. All the rest of the things I learned in geometry work just fine, except for parallel lines. Well, let's actually go back and visit triangles, but not triangles that we can draw on a sheet of paper, but triangles that we can draw on the Earth. So we need our computer to aid us one more time. And again, we start with our two dots. So let's draw a triangle. And then once again, you look at this picture and say, wait a minute, that's not a triangle. Well, actually it is, because let's continue our diagram. And once again, what we see is that we have now drawn a triangle on the surface of the Earth. So this ball you can think about as the surface of the Earth. The bottom of the triangle lies along the equator, and then the two vertical lines are drawn by going directly north and meeting at the North Pole. Now, once again, let's imagine that we take a compass out and we lay the compass so that we measure the angle on the left side of this diagram. We lay the compass out to measure the angle on the right side of the diagram, and we use the compass to measure the angle at the upper part of the triangle. If you add all of these angles together, in fact, you get something greater than 180 degrees. And so not just one part of what you understood about geometry is changing. We have now another exception. So now let's turn to circles, which will be our last illustration. Let's take, in fact, not the circle you're used to, but in fact a different kind of circle. Again, what I want you to begin to think about is not a circle that you can draw on a piece of paper, but instead a circle that we get by starting on the surface of the Earth. So imagine you're at the equator of the Earth. That's what our computer represents with this dot that we see in the image. And now, again, I want you to head directly north. And so you would start to walk like that. And finally, you'd reach the North Pole right here. But this time, instead of stopping at the North Pole, I want you to continue until you go back down to the equator. And now you've done that. Now, so you have this incredibly long line that you've drawn from the equator on one side of the Earth to the equator on the other side. Now, let's imagine that you and a friend take hold of this, let's imagine it's rigid. Each of you take hold of one end, one of you walks towards the west, and the other one of you walks westward. Then, in fact, you see an image that looks like this. The purple line is the pole that you held between the two of you, but when you get all the way around to where the other person was, you have described something that's kind of similar to a circle, except that there's something very curious about this object. This green dome that you see in this figure, the area of this dome is related to the length of the line. Now, you might wonder what that relationship is, and I will return to that shortly. Let me do this in a simpler case for you. Namely, let's do a real circle. So here, I again start with a dot. Now, before, when you were at the equator, I told you to walk north. Well, this is a flat plane, so now I'm just telling you, just start walking, and there you go. After a certain point, you decide to stop. And when you stop, then I want you to take that length of line behind you, hold its middle fixed, and then turn the line around that point. You describe a circle. And here we see it outlined in green. Now, the interesting thing about this circle is that if you ask for its area, there's a very famous formula which says that the area of the green is equal to 1/4 the number pi times the square of this long line from one side to the other. Now, we want to compare this with the dome figure that we talked about earlier. There, when we went from equator to equator, again we described a line. When we turned it around at the top, we held the North Pole fixed and rotated the line around the surface of the Earth. But now if you ask what's the relationship between the length of the line and the area of the dome, it turns out to be that that area is twice the one that you would find in the flat plane. So, something's very interesting is going on in this discussion. We have talked about standard things in geometry, whether it's straight line segments rotating on a plane, which leads us to a circle, the area of a circle, or if we do it on the surface of the Earth, we get something different. So you might say there's something very puzzling going on because, you see, all of those geometrical facts that you know I have actually shown can sometimes fail. Now, there was a point in history of mathematics when all mathematicians thought that the geometry that you learn in high school was taken as sacred. People thought, well, that's just the way it is. That's the way the world works. And there's only one notion of geometry. Well, what I've just shown you is that that cannot possibly be true. You see, in ancient times, we couldn't travel around the globe and do these kinds of experiments. But now that we can think about globes, we can see that there's something wrong with the notion that there's one geometry. If you do geometry on a plane, that's just as good as doing geometry on the surface of the Earth, or at least it should be equivalent. Now, there were four mathematicians, the group of four mathematicians whose names I have already given you earlier, and these were the first people who really started asking the question, is it possible that the properties of lines, triangles, and circles depend on the object upon which you draw them? In our computer-generated experiments, we see that that's, of course, true. It's exactly the case that every time we do something that we normally think about doing on the flat plane, if we carry out the same operation on the surface of the Earth, we get a different answer. The four mathematicians who I named were the first people who strongly understood that different answers depend on the shape on which the experiment or the measurement is taken, what you're working on. Now, even though they understood this, not all of them liked it very much. In fact, Gauss, who was one of these mathematicians, never publicly propagated the fact that he knew that there were other kinds of geometries. In fact, he named them non-Euclidean geometries. In fact, geometries that are not that of Euclid, which says that the rules of geometry are not as simple as you first learn in high school. Now, of course, this is actually very strange in the terms of history because the very word geometry means measuring the earth. And so it's rather peculiar that we start off knowing that geometry is about measuring things, but by the time that mathematics is very well developed, we forget that. So back in ancient times, we knew that geometry was related to measuring things. By the time of the Renaissance in Europe, we had forgotten this. We had gotten away from the idea of thinking about mathematics as being connected to the real world. Now, Mr. Riemann most aggressively and most completely addressed this point. Riemann showed that the different kinds of geometry that you get on a flat surface versus the geometry you get on the surface of a sphere are both mathematically equivalent. In fact, he wrote a new kind of mathematics to describe when the differences occur. He invented new mathematical objects, one of which was called the metric, the other is called the Riemann curvature tensor, and guess what? We're going to talk about both of these in much more detail later. In fact, they're going to be very important, but the mathematics is, well, fairly complicated. I'm going to show you, however, a little piece of it. Well, wait a minute. That's Einstein's equation. So how did that get in here? Why are we talking about Riemann and Einstein? Well, because what Einstein actually did when he talked about the curvature of the universe and the Big Bang was to borrow the mathematics of Riemann. So the mathematics was just laying around waiting to be used. But before Einstein picked it up, it was thought that this mathematics was only mathematics having nothing to do with our world. And so again, we can see this curious interplay between ideas that are thought to be purely subjective, purely imaginary, and all of a sudden they come roaring into our world. So that's the connection between Einstein and Riemann. When these equations were written, we began to get a new insight into our universe. It's from these equations and looking at their solutions that we scientists first came to understand the possibility of a Big Bang. Now, the Big Bang is not just a scientific hypothesis. We now have, in fact, observational evidence that the Big Bang occurred and that we live in a universe that is about 13.7 billion years old. Perhaps the most exquisite use of Einstein's theory of general relativity comes to us in the form of understanding gravity. Remember, string theory must conform to our understanding of gravity. Otherwise, we would say it's not physics. So let's review gravity. In this animation, which I'd like to play for you, there's a reddish object. I'm going to use this to represent the sun. It's in the center of the diagram. Out to the left of the diagram, you'll see the planet Earth, again represented by a little blue ball. And the circle inscribing the sun is the Earth's orbit. That's our orbit. And of course, the sun gives off light. So in this computer graphic, you'll see the sun's light represented by the slightly orangish glow about it. Now, it takes the Earth, of course, 365 days to orbit once around the sun. And I'm going to set my animation in motion now. And one thing to notice is, well, there the Earth goes. You'll notice that the light from the sun doesn't instantaneously come. I've drawn a slightly bright ring. It takes about 8 minutes or so for light to travel at roughly 670 million miles per hour from the sun to the Earth. Remember, this is really supposed to be mathematics. So let me do something that we can never do in real life. Namely, we can see our Earth orbiting quietly around the sun. The sun is glowing, it's shining nicely. Now, since this is mathematics, however, I have the power to change the equations. So I'm going to change the equations with the Earth at the location right now, and I've caused the sun to disappear. Now you'll notice when the sun disappears, a circle of darkness occurs. That's because in space, without the sun, there would only be darkness. Now this ring of darkness actually travels because it's the absence of light. And so you can think of it as that the back end of this ring are the last set of photons the sun sends out. But if you look at this diagram, there's something very funny about it. And at this point, if you look very carefully, you can see the ring of darkness has started to expand around the sun, but the Earth has already gone out of orbit. It's no longer traveling along the circular path. The sun has disappeared. Now, in our universe, typically when something happens at one place, there's a time delay before it is known someplace else. Yet in the equations that I just showed you, as soon as the sun disappeared, the Earth went flying out of its orbit with no time delay involved at all. The interesting thing about this situation is that it's an accurate representation of the mathematics that describes gravity if you believe Sir Isaac Newton. His equations about the force of gravity do not allow for a time delay. Yet, if something like string theory is to work, all of the forces must have a time delay. In fact, the equations are such that when something happens in our universe, according to Newton's law, instantaneously everywhere else it's known. Clearly, there's something wrong with Newton's picture versus the way our universe works. The remarkable thing about Newton's equations, however, is perhaps when we look at them, at least at his equation of gravity, it's without this property of time delay. Now, it's a well-known fact that even though his equations don't have the time delay, they're quite sufficient to figure out how to go from the Earth to the Moon. For example, we did that with Project Apollo. Now, the equations that govern this say that the force of attraction between the Earth and the Moon goes like the product of the masses divided by the square of the separation. And if you believe the stories, Newton was inspired to write this by having an apple dropped on his head. This equation has no role for time, and that's why there's no time delay. The time variable, as we physicists or mathematicians say, is just not in this equation. And so it talks about the force between the Earth and the Sun, or the Earth and the Moon, and it says that the repulsion, for example, between electrons, because we can modify this equation to describe the force of electrons, is instantaneous. Now, I'm sure that generations of high school physicists and high school students have learned that like charges repel each other, and they go by the product of the charges divided by the square of the distance. Very similar to Newton's law. But there's something rather interesting, because in the equations for the electromagnetism, you have to wonder, where does that delay in my drawings come from? Why isn't light instantaneously transported from one place to another? Well, the answer is that there is a time delay for light, and this answer turns out to be a manifestation of the fact that light is a manifestation of the electromagnetic force. It must have a time delay. In fact, in our previous picture where the sun suddenly disappeared, we saw the time delay, and that is the expanding circle of darkness, because the equations governing that were not the ones that say that there is no time delay. So you might wonder what's going on. It turns out that we know how to build a time delay into the transmission of light. This was first done in 1873 by a Scottish physicist named James Clerk Maxwell. Maxwell wrote 4 equations, and many times if you go on the college campus, you can actually see these equations on a t-shirt. It says, God said, let there be, and then the 4 equations are on the shirt. These 4 equations describe light, which is why the t-shirt is so popular among physics students. Maxwell's equations have built into them a time delay. We can even understand how this time delay works by looking at a few pictures. In fact, there's another physicist by the name of Richard Feynman who showed us this beautiful construct called a Feynman diagram, and it tells a story. It says, let's imagine that we had 2 charged particles, 2 electrons, which represent by the image that I have before you. Those are the 2 blobs of light. One electron moves through space and time and at a certain point sends a message carrier to the second. With the message, you ought to be repelled. If the message carrier travels at finite velocity, then there will be a time delay. And there is such a message carrier in nature. It's called a photon. The photon, the particle of light, it's the message carrier of the electromagnetic force. And that's why that region of darkness, when the sun vanished, traveled outward, and it travels outward with the speed of the last photon emitted. So time delays were built into electromagnetism in 1873. Einstein, in some sense, used this information when he worried about time delays in the force of gravity. Think about it. Newton was essentially starting alone. Einstein has the benefit of the work of both Newton and Maxwell. Newton's work on gravity, Maxwell's discovery of a time delay in the electromagnetic force. So what Einstein in some sense took on as a task was to look at both equations and realize that in order to build a time delay into gravity, there has to be a message carrier for gravity. And the message carrier is exactly whose mathematics? Why, it's Riemann's. So Einstein's mathematical equation that we wrote earlier, his theory of general relativity, is the equation that precisely does for gravity what Maxwell did for the electromagnetic force. It allows for time delays. We can see the difference between Newton's view of gravity and Einstein's view of gravity by looking at a slightly different graphic. Once again, we have our sun shining brightly. We can set our graphic in motion. And once again, by changing the equations, we're going to cause the sun to disappear. Now, this time, something slightly different is going to happen because the sun will disappear at this point. And you'll notice that the ring of darkness appears. However, the Earth continues to move in its orbit as if the sun had not disappeared. That's the time delay that we're talking about. The Earth does not yet know that the sun is gone. And now it is only when the ring of darkness, that represents the fact that the photons have gotten there, reach the location of the Earth, that we see the Earth go out of orbit. So the time delay, which we were desperately looking for, is part of Einstein's equations of motion. It says that there's a message carrier, and this message carrier is responsible for the time delay. So, what have we learned from all this? Well, according to Einstein, the speed of light is the secret to understanding the universe. He used the notion that the speed of light should be the same for everyone. This was, in fact, for him, a Rosetta Stone, and it stretched all the way back to his 1905 work and even to when he was a young teenager. Now, the great thing about the theory of general relativity is that it tells us the universe is consistent in a way that we didn't know about before. Nothing instantaneously can be communicated from one place to another. And even Newton suspected this in his great work, the Principia. Curiously enough, although Einstein builds time delays into gravity, Maxwell had tried to do this in 1877. So it tells us that space-time is flexible. It also tells us that there's a message carrier and that nothing can travel faster than the speed of light. So this is the great thing about Einstein's revolution. Building a mathematical theory of everything is a little bit like a parent on Christmas Eve and confronting one of those toys that says some assembly required. I don't know if you've ever had this experience, but if so, you begin by laying out all the pieces on the floor, and it seems like they cannot possibly all be important. You pick up the instructions, and as best as you can, you begin to assemble the toy. If you are lucky, every little bolt, nut or screw, and each piece of plastic, metal or wood will wind up in your completed construction. If at the end of your construction there remains a part, you might begin to worry. The more complicated the toy, the more likely the missing piece will ultimately lead to the disappointment of a child whom you love. Like the parent in the story, when we talk about the pieces of string theory, at first it seems like there's no possible connection. Like Gravity, the force of electromagnetism. Why are we talking about these things? Well, what we've been doing in this lecture is figuratively been laying the pieces and parts of reality out on the floor. These are the pieces and parts that you need for a theory of everything. Our universe is in fact like the most complicated toy whose intricate parts we can only hope to begin to understand.